Before we dive into Gauss' law, we have to talk about flux. And the question that comes up is, what is flux? Flux is the amount of something that passes through a surface, and that's a really general definition of it. We're going to give flux the symbol phi, which is the Greek symbol phi, which is also written this way with lines on the top. But I'm a little bit lazy and I like to write things a little faster, so I tend to omit those lines on the top and bottom. It's kind of like the idea of writing a capital I sometimes as a line and sometimes with bars on top and bottom. Anyway, so when we're talking about electric flux, we're talking about the amount of electric field that passes through a surface. And this is the focus right here. Later in the course, we'll talk about magnetic flux. Right now, we're just talking about electric flux. One way to visualize this is with electric field lines. So if we had electric field lines going off, say, to the right, then we could have a surface. And if I define maybe a square surface, so this would be a planar surface because it's maybe like having a sheet of paper, something flat. Then I could look at the number of field lines that are passing through that surface. And that would give me a numerical representation of the electric flux. And we know that where the electric field is stronger, there are more field lines, or where another way of saying that is where the field lines are denser, where they're closer together, the electric field is stronger. So counting the number of field lines, if you have a drawing that's actually sort of to scale and representative, the number of field lines passing through a surface really does give a good representation of a higher electric flux. Now, to calculate flux in general, it's actually defined by an integral, and it's a surface integral. And it's the surface integral of the electric field and then the dot product, dA. dA is a tiny piece of surface area, where the magnitude dA is the area and the direction is perpendicular to the surface and outward. And the units for dA, because it's area, are just meters squared. Then on the left-hand side, phi is the electric flux. And you'll often just call this the flux. Later on in the course, we'll look at magnetic flux as well, but you can just ignore that for right now. The units for the electric flux then are newtons meters squared per coulomb, which makes sense because you have newtons per coulomb in the electric field multiplied by meters squared, so you get a newton meters squared on the top and coulombs on the bottom. And just as an example of this, if you imagine a cube, so I can look at the top example, or the top surface, and have a little piece of area called dA. That would be on the top. The idea for the direction is that the direction of that piece would be upwards, perpendicular to the top surface, perpendicular to the area, and that would be dA. If we're looking at the right-hand side, I could define a little piece of area similarly and call that dA, and now I'm using color coding. This one is green, but the idea on this side is that it would be outwards and to the right. So again, it's perpendicular to the surface and then outward. And if I'm looking on the front, it would be a similar sort of thing. I can make a small piece of area, and this one, it's hard to always draw 3D on a flat screen like this, but the idea is that it would be coming out of the screen towards us. Now, generally, we calculate the flux as an integral. It's a surface integral. We're integrating over the entire surface area. And usually we set this up so that the math is really easy. Now, it turns out that for a constant uniform electric field and a planar area, this simplifies dramatically. When we have a constant uniform electric field, that means we can pull the electric field out of the surface integral. And then when we integrate along the surface area, we're just integrating dA, so we're really just going to get the total area. And because it's planar, it has the same direction everywhere. So we actually can simplify this down to the flux through that planar surface when that planar surface is in a constant uniform electric field is just the dot product of the electric field and the area vector for that surface. So the magnitude of that area vector is just the area. The direction for the area vector is perpendicular to the plane, or perpendicular to the surface. And because it's just a vector dot product, another way to write that is just the magnitude of the electric field times the magnitude of the area times cosine of theta, where theta is the angle between E and A. And so the tricky thing there really is just remembering that A is actually an area vector. So it's worth spending a bit of time on specific problems that test those ideas. And we end up using these two forms of the equation fairly often.